In this video, we're going to talk about factoring polynomials, giving a general strategy. So a general strategy to factoring polynomials. We've already discussed every single method there is to factor a polynomial that we're going to discuss in this course. And so now I want to put it all together and so that we can kind of tailor our thinking, the way we should kind of organize what we do when we see problems. All right. So we have factoring here. The first thing I do, no matter what problem I see, when I see a factor completely type instructions, is I'm going to first try to factor out the GCF. That's the first step of every problem. Of course, there's not going to be a GCF in every example, but that's the first thing I'm going to want to look for to factor out. After I factor out the GCF, I'm going to look and determine how many terms my polynomial has, because depending on the number of terms my polynomial has, there's a different method. For instance, polynomials that only have 2 terms, there's only 3 ways to factor it. It's either going to be a difference of squares, a difference of cubes, or a sum of cubes. And we know for a fact what those formulas that we'll be following in order for us to factor each of these 3 types of polynomials. All right. If I have a polynomial with 3 terms, there's only 2 ways to factor, right? I can factor the trinomials where 1 is the leading coefficient. Remember, when we do that, we immediately draw our double sets of parentheses, put our x in our first slots, and we find 2 numbers that multiply to give us c, but add up to that b, and those numbers are going to go in these second spots in these sets of parentheses. Remember, that's the binomials, right? Multiplies two binomials. When we have a number in front of the x squared other than a 1, what we want to do is we want to multiply a and c, right? We call this the rainbow method, okay? We multiply a and c, and we find 2 numbers that multiply to give us that a and c, but add up to the b. And what we're going to eventually end up with is 4 terms, and so we're going to end up factoring by grouping. And factoring by grouping is our last method, and that's the only method we know how to do when we have 4 terms after we factor out the GCF, grouping. All right? And so for the rest of this video, I want to look at examples where we use this chart to kind of help us tailor our thinking. Now, one thing that we have to remember is that sometimes after we do all of these factorings, we might have to repeat a process. And so what I like to tell students is that, hey, at the end, you need to make sure that you can't repeat any of these other things, because if you can, you're not going to have a polynomial that's factored completely. And that's the goal, is always to factor completely. In this example, I have in part 8x to the 3rd power plus 13x squared minus 11x minus 143. First step here is to factor out the GCF. Every single time I'm going to think of that. There is no GCF in this example, and so what I'm going to do is I'm going to count the number of terms. I have 1, 2, 3, 4 terms, and so when I have 4 terms, the only way to factor is to factor by grouping. And so what I'm going to do here is I'm going to group these first 2 terms together and the second 2 terms together. I'm going to factor out an x squared out of this first term. I'll be left with an x plus 13. And out of that second term, I can factor out a negative 11. And I'm also going to be left with x plus 13. All right. Notice that both of these terms have an x plus 13, so I can factor that out. And I'm going to be left with x squared minus 11. All right. And so I think I'm done factoring, but I got to check to see if I can repeat the process. All right, so if I look in this set of parentheses, there is nothing I can factor this out. It has 2 terms. There's no GCF. It's not a difference of squares, difference of cubes, sum of cubes. Same thing happens here. Although this may look like a difference of squares, right? 11 is not a perfect square, so I can't factor this any further. And that means that this polynomial is factored completely. Let's go to part B. I have x squared minus 10x plus 20. All right, again, the first thing I'm going to think about is determining whether I have a GCF. Looking at that polynomial, there is no GCF. Remember, there's not a number in front of the x squared besides 1, and this one doesn't have an x in it. There is no GCF. Now I'm going to count the number of terms. I have 1, 2, 3 terms. Remember, when you have a trinomial with 1 in front of the x squared, if you're going to be able to factor it, is going to be able to factor into two binomials where x's are in the first spots. All right. And so our goal is to find two numbers that multiply to give us 20, but add up to a negative 10. All right. You can think about that all day long, but you'll never find two integers where that works. And so this polynomial can't be factored. And remember, when we say a polynomial can't be factored, we call it prime. So this polynomial here is prime. Our next example is 4x squared plus 56x plus 192. All right, if I look at this example here, first thing I want to think about is factoring out a GCF, right? If I look at this example, I do have a GCF, right? My greatest common factor here is 4. I can factor out a 4. Out of that first term, when I factor out the 4, I'm going to be left with just x squared. Out of that second term, I'm going to be left with 14x. And out of that third term, I'm going to be left with 48. All right. So although this one looked like a trinomial with a leading coefficient of 4, after I factored out the GCF, now my leading coefficient is 1. And so if I want to continue to factor, I'm going to factor into two binomials, x in my first spots. And I want to find two numbers that multiply to give me 48, but add up to 14. Those two lucky numbers are a positive 6 and a positive 8. All right. Again, I can't factor completely any further in this x plus 6 here, and I can't factor any further here with the x plus 8, so I don't need to repeat any processes here. All right, let's go to part D. In this example, I have negative 10x squared plus 70x plus 180. Again, the first thing I'm going to think about is to determine if I have a greatest common factor. And in this example, my greatest common factor is 10. And since my leading coefficient is negative, I'm going to factor out a negative 10. And so when I factor out the negative 10, I'm going to be left with an x squared. Notice 70 divided by negative 10 is a negative 7x. And 180 divided by negative 10 is a negative 18. Okay, now that I have that, notice here, there's a 1 in front of my x squared inside of that parentheses, right? And so when I want to factor that, it's going to factor into two binomials. X's goes in the first spots. And I want to find two numbers that multiply to give me negative 18, but adds up to negative 7. Those two numbers will be a negative 9. So I'm going to do a minus 9 and a positive 2. All right. Check to see whether I can factor. X minus 9, I can't factor that any further. And the x plus 2, I can't factor that any further. So I know I'm done with factoring in that example. Let's look at some other examples. All right, in part E, we have 21x squared plus 31x plus 4. All right, in this example, what we want to do is we want to factor completely. All these examples we're factoring completely. All right, first thing I'm going to look for is to determine if I have a GCF. If I look at all these three terms in this polynomial here, there is no GCF. All right, so the next thing I'm going to do, right, we just said that we have three terms and there is not a 1. There's a 21 in front of our x squared as our leading coefficient. And so this one, we will use our rainbow method. I'm going to multiply 21 and 4. 21 times 4 is 84. And so I want to find two numbers that multiply to give me 84, but add up to this 31. That's my middle term. And those two lucky numbers will be 3 and 28. So what I need to do now is I need to write this 31x as a 3x plus a 28x, right? And so we get 21x squared plus 3x plus 28x plus 4. Right? And by doing that, we now have four terms. These two terms here and those two terms there, we're going to factor by grouping. That first grouping, I can factor out a 3x. I'm going to be left with a 7x plus 1. Out of the second grouping, I can factor out a 4, and I'm going to be left with a 7x plus 1. All right? Notice the 7x plus 1s here. We can factor that out. So I'm going to have an 7x plus 1 times a 3x plus 4. All right. Notice here at the end, I can't factor anything out of this 7x plus 1 or that 3x plus 4. There's no techniques that will help me factor that further. And so I am done factoring in this example. Let's go to part F. I have a 5x squared minus 125. Again, the first thing I want to think about is whether I can factor out a GCF. In this example, I can. My GCF here will be 5. If I factor out a 5, I'm going to be left with an x squared minus 100. Sorry, it's not going to be a 125. It's going to be a 25 here. X squared minus 25. All right. Notice here I have two terms inside of this parentheses. So when I have two terms, I only have three ways to factor. Difference of squares, difference of cubes, sum of cubes. All right. Since this is a subtraction, I know it's going to be a difference. And since this is a 2 as my exponent here, I know it's going to be probably a difference of squares, all right? But I got to be careful. I got to make sure that this number right here is a perfect square, and it is the same thing as 5 to the second power. And so if I want to factor that, remember the formula for a difference of squares is a squared minus b squared equals a plus b times a minus b. So the thing that I'm squaring here is the x. The thing that I'm squaring here is the 5. So this is going to be a plus x plus 5 times x minus 5, and we'll have that factored completely. And so this is going to be a 5 times x plus 5, x minus 5. All right, let's look at some other examples. Part G, all right, I have a 27x to the 9th minus an 8y to the 3rd. All right, this example here looks complicated. First step I'm always going to think about is GCF. Right? If I look at this example, there is no GCF between these terms here. And so next, I count the number of terms I have here. I have 1, 2 terms. And so the only way to factor when I have 2 terms is to see a difference of squares, a difference of cubes, or a sum of cubes. Of course, it's going to be a difference since I see a subtraction. But is it going to be a difference of squares or a difference of cubes? Whenever I have exponents that are other than 2 for squares and 3 for cubes, I've got to now think of multiples of 2 and 3, all right? Or we got to think about numbers that are divisible by 2 and 3. Notice that this 9 here and this 3 here are divisible. They're both divisible by 3, all right? That's a sign that I'm going to have a difference of cubes here. All right, when I have a difference of cubes, I got to remember the formula. A cubed minus b cubed equals a minus b times a squared plus ab plus b squared. That's the formula that I have to remember. And so to really know whether I have a difference of cubes is to look at the coefficients. Notice that 27 is a perfect cube. It comes from cubing 3. And 8 is a perfect cube. It comes from cubing 2. And so what I can do is I can rewrite this polynomial so that I can see the a cubed minus the b cubed here. All right, 27 is 3 cubed. What do I cube to get x to the 9th? One way to figure that out is to actually divide this 9 by 3. And if I divide that 9 by 3, I'll get a 3, right? And so this is actually 3x cubed raised to the 3rd power, all right? Now I'm going to go to the 8y cubed. 8 is the same thing as 2 to the 3rd power, and y to the 3rd power is y to the 3rd, right? And so these are my a, right? So my a is this 3x cubed here, and my b is this 2y here. So in this formula, I'm going to put them in their respective places here, all right? And so let me give myself a little more space. So if I use my formula, it's going to be a 3x cubed minus a 2y. That's the a minus b part. And now I'm going to do the rest. Times, I'm going to use a parentheses here, 3x cubed squared plus a 3x cubed times a 2y, right? Because 2y is my b, so this is my a times b part. Plus a 2y quantity squared. That's my b squared part of my formula, all right? And so the rest is just simplifying, right? And so if I continue to simplify, this parentheses is going to stay the same. And the other parentheses, 3 squared is 9, and if I square the x cubed, remember you multiply those exponents, so I get x to the 6th plus 6 x cubed y plus 4y squared. All right, you square the 2, square the y, and you get the y squared. And that is factored completely. Notice here, I can't factor these two terms here. It's not a difference of squares or a difference of cubes. And I always told you that once you try to factor out the GCF, this part right here will never be factored anymore. And so this is my final answer to have that factored completely. Let's go to part H. In part H, I have a 49x to the 4th minus an 81y to the 10th. All right, first step, once again, factor out the GCF. If you look here, there is no GCF. Now I'm going to count the number of terms I have. I have one term here, another term there. So 2 terms. So difference of squares, difference of cubes, sum of cubes. Of course, it's not going to be a sum. It's going to be a difference. So I got to figure out whether I can factor this using the difference of squares formula or the difference of cubes formula. All right. In this example, notice I don't see 2's as my exponents, or I don't see 3's as my exponents. So I got to determine if these numbers are divisible by 2 or 3. And if I look at this example, both 4 as this exponent and 10 as that exponent are both divisible by 2. All right. Since they're divisible by 2, that's a sign that if I'm going to factor this, it's going to be a difference of squares. To top that off, look at these coefficients here. I have a 49 as a coefficient and an 81 as a coefficient. They're both perfect squares. And so I'm going to factor this just like I'd factor a difference of squares. Well, we need to see what we're squaring here in this difference. And so I'm going to rewrite this. Of course, you square 7 to get 49. And the exponent on the x, when I square this, is what I get when I divide this exponent by 2, since it's divisible by 2, right? 4 divided by 2 is 2. And so the first thing I'm squaring in order for me to get a 49x to the 4th is 7x squared. I'm going to do the same thing for the 81y to the 10th. If I square a 9, I get y squared. And if I square a y to the, let's divide this 10 by 2 here. 10 divided by 2 is 5. I get y to the 5th, right? And so we already stated the formula for a difference of squares, a plus b times a minus b. So if I'm going to factor this, it's going to be an x squared, 7x squared plus 9y to the 5th times a 7x squared minus a 9y to the 5th. And that's how I factor that example. Let's look at one other example. This example I here is x to the 4th minus y to the 4th. All right. This example here is very similar to the last example. Notice there is no GCF. There's 2 terms. And if you look at these exponents here, they're both divisible by 2. All right. In order for me to get x to the 4th, I square x squared. Right. I got that from dividing this 4 by 2. And in order for me to get y to the 4th, I square y squared. Right? Divide 4 by 2, you get that 2. Right? And so this is the difference of squares. And the difference of squares, right, we have a squared minus b squared equals a plus b times a minus b. So I can write this as x squared plus y squared times x squared minus y squared. All right? And so I factor that, right? Now I got to make sure that I can't factor any further, right? This is an x squared plus y squared. That's 2 terms. There's no GCF there, but that's a sum of squares. And we always said that a sum of squares is prime. We cannot factor a sum of squares. But if you look here, I have x squared minus y squared. That's 2 terms. There's no GCF, but this is a perfect square. And that's a perfect square, right? So this is a difference of squares once again. And so I have to continue this process or repeat this process in order for me to factor completely, right? And so I'm squaring an x here, and I'm squaring a y here. And so if I continue to factor, this is going to factor into an x plus y times an x minus y, using my difference of squares formula on this part right here to go further. All right. So in this example, this is a prime example of when we need to repeat the process. Of course, we can do the initial difference of squares when we're looking at the initial polynomial. Once we get that into factored form, We once again check to see if we can factor. This binomial here can't be factored, but this binomial here can be factored, and it's factored using the difference of squares formula once again. And once we did that, we got the x plus y times the x minus y, and now that is factored completely. This concludes our video on a summary of factoring polynomials.